Today, we're uncovering the hidden chemical forces shaping the foods we eat every single day. We are talking about microscopic engineers performing absolute feats of physics and chemistry right under our noses and, well, right on our taste buds.
Is something we totally take for granted, right? How do things like mayonnaise, ice cream, margarine, and chocolate stay so perfectly mixed when oil and water naturally want nothing to do with each other? We all know that visceral conflict. Pour oil into a glass of water and they immediately retreat into their own corners. So to keep these incompatible liquids locked in that perfect, creamy embrace, we need an invisible protagonist.
So here's our roadmap for this explainer. We're going to dive into the science of food emulsions, exactly how food emulsifiers work, and their major types. Then we'll look at the constant battle of emulsion stability and destabilization, check out some real-world food applications, and finally wrap up with regulation, safety, and beyond.
Let's kick things off with Part 1, the science of food emulsions.
In food science, we are primarily dealing with what are called macroemulsions. Basically, a macroemulsion is a heterogeneous system where one liquid is intimately dispersed into another as fine droplets, usually bigger than 0.1 micrometers in diameter. But the absolute most crucial phrase to remember here is thermodynamically unstable. These systems are fundamentally chaotic. They are constantly fighting to separate back out, meaning additives are literally required just to attain a basic acceptable shelf life.
This dynamic gives us two main environments. First, we've got oil and water emulsions, or OW, where oil droplets are dispersed throughout a continuous water phase. This is the exact magic behind mayonnaise and creamy salad dressings. And then you contrast that with water and oil, or WO, which are inverse emulsions. This is where water droplets are trapped within a continuous oil phase, and that creates foods like butter and margarine.
Moving on to Part 2, how food emulsifiers work.
So what actually is an emulsifier? You can think of it kind of like a microscopic diplomat. They are surface-active molecules with a complete dual personality. One end features a hydrophilic, or water-loving head, while the opposite end has a lipophilic, or oil-loving tail. Because they have this unique affinity for both, they perfectly bridge the gap between those totally incompatible aqueous and lipid phases. They rush straight to the interface between the two liquids and drastically reduce the interfacial tension. Let's break down the mechanical and chemical steps of how an emulsion is actually born. First up is the initial dispersion of the phases, and this usually happens through vigorous mechanical agitation. That mixing causes surface deformation and, eventually, droplet disruption. But actually breaking a liquid down into tiny droplets is incredibly difficult because of a physical phenomenon called Laplace pressure. And this is exactly where our emulsifiers shine. They lower that Laplace pressure, which makes droplet disruption possible in the first place. Finally, the emulsifier partitions into the interface, locking those newly formed droplets in place before they have a chance to recombine.
Just to put this into perspective, when you create an emulsion, you are increasing the surface area between the liquids by up to 1,000 times. Just imagine the immense thermodynamic work required to create all that new surface area. Without emulsifiers stepping in to drastically reduce surface tension and offset that massive energy cost, keeping those droplets separated would be virtually impossible.
Which brings us to Part 3, major types of emulsifiers.
Let's look at a couple of the major players. Consider phosphatidylcholine. It's a major component of commercial lecithin and a primary naturally occurring emulsifier extracted straight from soybeans. Now compare that complex natural molecule to a synthesized monoglyceride. Mono and diglycerides are actually the most commonly used food emulsifiers globally. They're synthesized by reacting glycerol with triglycerides, making them highly effective, extremely straightforward, and deeply reliable for food developers. Next up, we have polysorbates. These guys are synthesized by polymerizing ethylene oxide onto sorbitan fatty acid esters. They are incredibly effective, non-ionic, hydrophilic emulsifiers. In the commercial food world, polysorbates are the heavy lifters. They are heavily utilized in the commercial bakery industry specifically as anti-staling agents. And this one is just absolutely fascinating. Sucrose fatty acid esters. We are essentially looking at common sugar that has been esterified with fatty acids. What's so amazing about this is the customizability. Just by tweaking the degree of esterification, like adding more or fewer fatty acid tails, food chemists can completely alter the molecule's functionality. For example, a sucrose monoester is a fantastic oil and water emulsifier, while a diester works much better for water and oil systems. It's literal precision chemical engineering.
Let's dive into Part 4, emulsion stability and destabilization.
So let's meet the villains of our story.
These 5 mechanisms are the relentless thermodynamic forces constantly attempting to tear our perfect mixtures apart. We've got flocculation, which is when droplets start clumping together. Coalescence is when those clumps actually merge into a single larger drop. Creaming, or sedimentation, happens when droplets rise or sink purely due to density differences. Oswald ripening is this crazy process where larger droplets literally devour smaller ones to reach equilibrium. And finally, phase inversion. That's when the whole system completely flips inside out. This microscopic chaos is exactly what dictates a product's shelf life.
So, how do our microengineers actually fight back against all that? Well, emulsifiers don't just sit there. They create physical, viscoelastic barriers right at the interface. They can form these complex liquid crystalline mesophases, which act like molecular armor wrapped around each droplet. On top of that, ionic emulsifiers utilize electrostatic repulsion. Following what's known as the DLVO theory, they give each droplet an electrical charge, causing them to literally repel one another, completely stopping coalescence in its tracks.
Now, let's zoom out a bit for part 5, real-world food applications.
Emulsifiers do so much more than just mix liquids together. They engineer the very texture, structure, and freshness of our food. In whipped toppings, they trap air for aeration. In bread, they actually complex with starch molecules, sliding right into the helical portions of amylose to soften the crumb and severely delay staling. In chocolate, they modify fat crystallization so you don't get that weird white bloom on the surface. They are fundamental architectural tools for food.
And taking this from a lab scale to an industrial scale requires some truly incredible physical engineering. You can't just use a standard kitchen blender to make industrial quantities of mayonnaise. Food scientists use intense equipment like colloid mills, which shear liquids between a rapidly spinning rotor and a stator, with tolerances of literally 1/1000th of an inch. Or they use homogenizers, which force these liquids through tiny orifices under massive pressure, utilizing extreme turbulence and literal ultrasonic cavitation to smash droplets down to sub-micron sizes. Which brings us to our final section, regulation, safety, and beyond.
Emulsification is a profoundly interdisciplinary science. The exact same thermodynamic principles, the same hydrophilic and lipophilic balancing acts that stabilize your creamy salad dressing are utilized in life-saving pharmaceuticals. We see this exact science applied in cosmetics, advanced drug delivery microemulsions, and massive industrial formulations. Food science here is fundamentally tied to biotechnology and biomedical engineering. And because these compounds are so incredibly vital across multiple industries, their deployment is deeply rooted in rigorous scientific evaluation and strict regulatory approval. Quality control relies heavily on advanced analytical chemistry. We are talking about high-performance liquid chromatography, gas chromatography, and even matrix-assisted laser disruption/ionization time-of-flight mass spectrometry, or MOLY-TOF-MS for short. This kind of heavy-duty testing ensures that every single emulsifier used meets exact safety and functional specifications.
Ultimately, emulsifiers really are the invisible engineers of our modern food systems. They serve as this incredible chemical bridge between biology, physics, and engineering, working tirelessly against the fundamental laws of thermodynamics to create the safe, stable, and enjoyable products we rely on every day.
Which leaves us with one final thought to ponder. If a few microscopic molecules can fundamentally change the physical nature of the food sitting right on your plate, what other invisible chemical forces are quietly engineering the world around you right now? Keep asking questions, keep exploring, and we'll see you in the next explainer.